In earlier sections, we've introduced the equations for force and electric field, and now we're going to introduce the equation for voltage. As you remember from a previous section, force is equal to K times charge 1 times charge 2 over R squared. K, we know, is 9 times 10 to the 9th newtons per meter squared per coulomb squared. Q1 and Q2 are the magnitudes of the two charges, and R is the distance between the two charges. The distance between the two charges is R. Now, if the two charges had opposite sign, if one was positive and one was negative, the two charges would be pushed together. If the two charges have the same sign, they are both positive or they are both negative, then they will be pushed apart. When we're solving problems involving this equation, we should use this equation, but we should think to ourselves, do they have the same sign or do they have different sign? And we should say, okay, if they have different sign, they'll be pushed together. So I know the force of Q2 is going to be this way, pushing it this way. And then I use this equation to get the magnitude of that charge. The magnitude of that force. Alright, and the second equation we learned is for electric field. And we know that the equation for electric field is K times Q over R squared. Force, of course, the units are newtons. And we found out that the units of electric field are newtons per coulomb. This makes sense. These equations are very similar, but they are different because for electric field, there's one less charge in the numerator. We lose a C, so we have to add a C to the denominator for electric field. The electric field tells us what the force will be on a charged object that is in this field. If it is a positive charge, it will follow the directions of the arrows. However, if it is a negative charge, it's going to move in the opposite direction of the arrows. So if I put an electron right here, which has a negative charge, the force on it is going to be this way. If I put a proton here, which has positive charge, the force is going to push it this way. When solving problems involving this equation, I should figure out what the values are for Q and R, input the numbers into the equation, solve for E, and then look at the diagram and figure out what directions are the arrows pointing and what is the sign of my charge. Today we are going to introduce a new equation, and that equation is for voltage. Voltage is equal to K times Q over R. And we know that for voltage, we use units of volts. And a volt is equal to a joule per coulomb. We know that the units for joules is Newton meter, which means that volts equal to joules per coulomb is equal to Newton meters over coulombs. Now compare these two equations. They are exactly the same, except we are lost an r in the denominator of this equation compared to this equation, which means we have to add an m to the numerator right here. This voltage graph and this equation tells us what the potential energy of a charged particle will be based on the location in this field and the magnitude of the charge. We increase the charge, we also increase the potential energy. These lines represent equipotential surfaces. Equipotential surfaces are surfaces that have the same electrical potential, and we know from the previous section that electrical potential is voltage. So the key takeaway from this section is this. What I want you to get from this section is this equation and this graph.